The next one comes as a electrochemical energy storage. So, what we have discussed till now is mechanical energy storage. So, next one comes as a electrochemical energy storage, and in that the battery energy storage system. And when I say battery energy storage system, mostly it comes down to the lithium ion battery storage system. And we have already talked a lot during our EV class. We have talked as a whole full chapter, fundamentals of battery pack design, and it's quite similar to that, except that it's for stationary application and the large size application. So, what we have is a battery system, then we have a power conditioning system, we have energy management, and how do we make the battery from the cells, BMS and thermal management, we make modules, then from that whole battery pack, then it could be a standardized solution like a container of 1 megawatt hour, or a custom solution like a small building where I want only 100 kilowatt hour, maybe some 500 kilowatt hour, something like that, and clubbed together this becomes a battery system. And one way we have an energy management system, other side we have a power conversion system. In a battery pack, multiple cells connected in series and parallel combination, parallel and series combination to provide required voltage and capacity. Then we have a battery management system, and then we have a battery thermal management system. Then we have energy management system where IT cloud monitoring unit, then you need to capture the data, and then energy management system which is responsible for energy flow, its management and its distribution. Then you have a conversion unit, bidirectional converters mostly, which has power electronics, converts the power flow between grid and the battery and the utilities. So, grid connection for utility scale mostly consists of multiple battery banks, like multiple container placed at one place, and that all adds up to the total energy storage and power. Then you have power electronics to individual as well as combined battery packs, or these battery packs can be combined in parallel to a common direct DC bus and can have electronics which is taking and giving the power from that DC bus. So, either you can have individual units or you can combine all the units together and provide the electronics at the or converter system at a whole, or can have a conversion system, power conversion or conditioning system at each unit of the unit, and that depends upon the cost, capital investment and the requirement of that particular place. Both the architecture is being used in the industry. Connection to the higher level grid by a transformer where you can step up, step down the voltage level and feed it to the grid. What are the advantages? It allows the round trip efficiency is more than 95%. You have hardly 5% losses. That's a big advantage. It's the power fluctuation and the capacity both are many of the time interrelated. Whenever you have excess power, quickly you can store it. Whenever you have reduced power, you can quickly take out the power from that. It helps in reducing dependency on the grid power always, can be installed at a small home level also and can be installed at the power generation unit also. Both the places it is possible. The small home, a small energy storage at the generation unit level, large grid storage. Much lesser carbon footprint for an individual, high initial cost, but cost is coming down day by day. It needs proper thermal and electrical design to ensure the system is safe always. Monitoring is very important because the monitoring helps you to increase the life of battery energy storage system and thus reduce the overall cost per unit energy. Regenerative fuel cells, so another electrochemical device. Hydrogen goes in at the anode Now it's keep and combines with you have a catalyst, combines with oxygen, gives you electricity, and H2O comes out. On other way, H2O comes out, it's get dissociated with in the form of oxygen and hydrogen when you provide the electricity. So that's why it becomes regenerative fuel cell storage. Electrochemical conversion device that produces electricity without combustion but by combining H2 and O2 to produce water and heat. It produces electricity from the fuel and also it takes electricity to produce H2 and O2. So this is the chemical reaction. Here H2 4H plus 4 electron, O2 plus 4H plus 4 electron, that becomes 2H2O. Net reaction is 2H2 plus O2 goes to 2H2O. So what you can do whenever you have excess energy, you can do the water electrolysis, generate, convert H2O into, in the last slide this is basically converting hydrogen and oxygen combined to the H2O and then gives you electricity. In the next process, how does it work? Whenever you have excess renewable energy, then you have a water electrolysis process which converts H2O into H2 and O2. Then you can store this H2 rich. Okay, I don't have idea what is LOHC, we will come back. So hydrogenation we do and then we convert back this into chemical energy and can store. Now this storage can be used for transportation, distribution and all those things, and can be, and then the same H2 can be utilized for the fuel cell and then you get the power. So what you do from the renewable energy, you do the electrolysis, you convert H2O, O2 goes directly to the atmosphere, H2 you have, now you need to store this H2 by process of hydrogenation. You store this in a chemical as a form of chemical energy storage system where H2 is in very rich form. One of them is ethanol. You can convert it into or ammonia NH3 solution. So where you have a high energy density of H2 and also less risky. Transportation becomes very easy. Then you store it and then you can transport it wherever you want in the world, can utilize as a fuel also there, or similar to our LPG gas, something like that. You can also fill, then dehydrogenation. Now you get back the hydrogen here and that hydrogen can be used in the fuel cells in the vehicle level. So here ammonia solution can be used for hydrogenation, here something else can be used for dehydrogenation. So that's how regenerative fuel cells energy storage works. There are various type of fuel cells: alkaline fuel cell, phosphoric acid, polymeric electrolytic membrane cell, solid polymer, proton exchange, and I would like you people to go through these all the things if you are interested in the fuel cells. So this is based on the electrolyte, then based on the type of fuel and oxidants like hydrogen and oxygen fuel cells, hydrogen rich gas air fuel cells, ammonia air fuel cells. Ammonia air fuel cells, then we have synthetic gas air fuel cell, hydrogen carbon gas. So this, even the hydrogen, when we talk, there are different types of hydrogen: black hydrogen, brown hydrogen, green hydrogen, which Professor Ashok has already talked about that. I will not go through much on that. What are the advantages and disadvantages? It does not produce any CO2 during whole of its operation. So I take renewable energy, I do electrolysis H2 and O2, hydrogenate it a system like you can have ammonia, which can be easily used for transportation and distribution. Again, I dehydrogenate it, get H2, can use fuel cells and can run the vehicle, I get H2O. So, there is no CO2 involved in this if I am using the renewable energy source. Disadvantage, if I use for hydrolysis or for making the hydrogen with natural gas powered plant, then that is a problem. Storing hydrogen is a big issue, and that is why we try to utilize something like ammonia for transportation. Hydrogen fuel cells are generally less efficient than the lithium ion batteries. So, these are the disadvantages. Around 60% efficient hydrogen fuel cells are. However, lithium ion batteries are as efficient as 95%. Flow cells or redox flow batteries. One of them is vanadium redox batteries, which is right now presently used at many places. It stores energy within the electrolyte of the battery and are the most mature type of flow batteries available today. Lot of work is going on other batteries, but as of now this vanadium redox batteries are the most mature type of flow batteries. How does it works? This stores in vanadium redox couples that are kept in two separate electrolytic tanks. Here two separate electrolytic tanks. Now, this electrolytes flow through the battery during the charging. This vanadium ion accept electrodes at the anode and deposit electrons at the cathode. So, there is a semi-permeable wall here which allows the electron transfer. The reactions runs in reverse direction when the battery is discharging. So, after a certain time when battery get discharged, you again charge it, discharge it. Similar principle of lithium ion storage, but the life cycle of this vanadium storage is much more than the lithium ion storage. So, this both the electrolytes is basically separated by a thin membrane which permits only ion exchange, not mass exchange. What are the advantages? High energy storage capacity, so it can run for high duration. Long life, thousands of the cycles it can run. Thermally very safe, you do not have to worry too much about on the thermal issues. Self discharge is not significant. It can recharge very quickly. If you provide, that means the power density is very high for the charging process. The two electrolyte solutions are chemically identical, which makes the operation of the battery much simpler and less expensive. What are the disadvantages? There are still some disadvantages. Low electrolyte stability and solubility, which can over the time can lead to the decreased energy density in the battery. The operating cost for BRVs is quite high and not very economically viable as of now. In future, a lot of flow redox batteries are going to be worked out. When I say redox battery, it is also like zinc air, aluminum air, these all are redox batteries, but technologies are being developed in such a way that the charging and recharging process can be separated out and could act as a long storage, just replacing the fuel, something like in the nuclear reactor what we do. However, in nuclear reactors we cannot recover the fuel. Here we can, by charging process, we can always recover the fuel. Next is superconducting magnet energy storage. It is a phenomenon exactly zero electrical resistance. If you keep bringing down the temperature and expulsion of magnetic fields occurring in certain material when cooled down below a characteristic critical temperature. Such type of metals are called superconductors. Superconducting magnet energy storage. Conductors for carrying the current operates at cryogenic temperature, very low, minus 100 degrees centigrade, or I can say in the Kelvin, 100 Kelvin, 50 Kelvin, 150 Kelvin at that temperature. And in such cases, it virtually does not have any resistive losses when it produces the magnetic field. The current in the coil can flow for infinite time. Time constant tau L by R, where R tends to 0, resistance tends to 0, inductance is there, so tau tends to infinite. The energy stored is inductive. What are the components? Superconducting magnet with the supporting structure. What we have here is the cooling circuit. It's basically the motor and turbine system, how to get back the energy. It's a cooling circuit here. It's a cooling circuit here which maintains the temperature to the cryogenic temperature. What are the things we have? Superconducting magnet with the supporting structure, cryogenic refrigerator or cryogenic system, that is what it is here. Cryogenic refrigeration system here. Then we have a power conditioning system, and then we have a control system. This is how it looks like. Superconducting coil, then you have a coil protection and all those things, then you have a refrigeration system here, then you have a control circuit, and then you have a power conditioning system. So you see, low temperature superconductor magnet, critical temperature is below 30 degree K. There are some high temperature superconductor magnets also available, 77 K Kelvin. So you are at basically minus 150 degree, minus 200 degree centigrade level. So somehow this high temperature superconductor, if something we can bring it down to 10 degree centigrade or 0 degree centigrade or minus 20 degree centigrade or minus 40 degree centigrade, it would become quite viable. As of now, because of the temperature requirement, only on the very high end research lab this is being used. The material what we use is niobium and titanium alloys, but this is required to be operated at 4.2 K. It's a very low temperature. Despite good working, it's very expensive in terms of investment and operational cost as of now. So it doesn't work out great till now. In future, when technology improves, it should work out well. Most high temperature superconductors are ceramic material like bismuth, strontium, calcium, copper oxide, BESS, CCO it is known as. But yes, a lot of technology need to be developed in this field to utilize it to the mass level. What are the advantages? It can be recharged in minutes. That means power density is very high. Literally no loss of power because you don't have any resistance anywhere. Future power storage that may produce zero carbon emission can be utilized using this, but today, yes, not a very good option. Requires very large space. Large magnetic field could possibly, if I start using for large storage, it could possibly interfere with the earth magnetic field. Those are possibilities which will be certainly worked out in the future to make it viable. Supercapacitor. The capacitor stores energy by collecting positive and negative charge on the two conductive plates opposite one another and separated by a dielectric material. This dielectric could be air, could be some other material. Now an electric field formed between two plates that can be used quickly to store and release the energy. So that's we say capacitive energy. So you have a cathode, you have an anode, and then you have an ionic liquid. That's a double layer capacitor. So these are the supercapacitor UPS. Somewhere it is being used. In fact, I have in a home emergency light which uses the supercapacitor as energy storage. It gets charged through the solar panel, can give around 4 to 6 hour energy. The advantage is it has a very high cycle life. Why we say supercapacitor? Generally it has the energy storage or energy density 100 times greater than the conventional capacitor, and that it stores the energy between two high surface area electrodes separated by ion permeable members. An electrolytic solution is used many of the times between these two electrodes. The large surface area supercapacitors allows the higher energy density but has its own drawbacks like lower power densities compared with the conventional capacitors. Compared with electrochemical batteries, supercapacitors could be characterized as having high power density and low energy density depending upon the users. So, what is the energy? Half CV square, where C is the capacitance and V is the voltage across the plate. Optimal capacitance C is epsilon naught area by D, where epsilon naught is the area of the plate, D is the distance between the two plates. How to increase the capacitance? Increase the surface area or reduce the separation. Both way it is possible. What are the advantages? Virtually unlimited cycle life. 1 lakh, 1.5 lakh, 2 lakh cycles is very easy. Excellent low temperature, it does not get impacted with low temperature much. However, with the lithium ion batteries, the low temperature is a problem. It is a cost effective, can be charged in the seconds, can be easily disposed because most of the materials are common materials available. Problem is it has very low specific energy density. Power density is very high but very low energy density. Linear discharge, if it's keep discharging, voltage keeps on coming. So, you cannot utilize the full energy spectrum. High self discharge, that is another problem. The cell voltage is very low, around 2 volt, that is another issue. Presently it has high cost per watt, and that is what it is getting prevented for not being utilized commercially at high rate. Mainly two reasons: very low specific energy, very low specific energy density, and the high cost per watt. The two reasons dominantly make it not to be usable at the larger scale as of now. However, several places it is being used because of virtually unlimited cycle life.